All right. So first of all, quick announcement on your labs. Lab one, I think I got a few questions whether there is a specific format that you need to follow for the report. There is no specific format. Just put your screenshots from your measurements or whatever simulations you're doing on your report, and that should be all. So you just copy and paste the question, and then whatever you have done to perform that particular lab or that particular experiment. So it does not need to be any particular IEEE format or anything. It just needs to be there. So as long as your EPAs are happy with it, it should be fine. Okay, there's no specific format. Regarding lab two, I have heard that some of you had delays in the components arriving, but I hope all of those components are arriving early this week at least, so that you get enough time to start with your pre-labs for lab two. And that's why you're starting lab two next Monday. So that is next week, instead of starting it this Wednesday. Okay, because there's very little time till this Wednesday for you to start working on your pre-labs. We'll start on a Monday, we'll finish by Thursday. So that's what it's going to be for most of these labs. So this week, Wednesday and Thursday, there will be no labs officially. But if you were not able to complete some part of lab one last week, please work with your TAs or EPIs so that you are able to complete it by this week. Okay, but officially there will be no labs on Wednesday and Thursday this week. And we're going to resume with lab number 2 from Monday next week. Any questions? Yeah.
Are error measurements necessary?
Error measurements are not necessary. It's not asked in the question, right? But so just go through the document that if it is not asked in the question, it's not necessary. All right. Now, for the last 2 to 3 lectures, we have been discussing op-amps. It's just basically this 3-terminal device where you have a positive input terminal, a negative input terminal, and an output terminal. Ideally, input impedance is infinite, output impedance is 0, the gain is infinite. But as you'll see in most of the lab experiments, as well as homeworks later on, the op-amps will not be ideal. And that's what we have learned through the loop gain analysis, that how to analyze non-ideal op-amps. And we have looked into it from multiple different perspectives. We have looked into how to solve KCL and KVL around a circuit that involves op-amps. We have looked into the feedback-based analysis that basically gives you this equation and 3 forms of the same. Right, so you have 3 different forms of the same equation that basically eventually gives you this, that your closed loop gain is A infinity, which is the gain of the system, assuming that the op-amp is ideal, divided by 1 plus 1 over T, where T is your loop gain, that is your gain of the op-amp multiplied with beta, that's the feedback factor. Okay, so whenever you are doing non-ideal op-amp analysis, we'll be using this formula. And we have looked into...
excuse me. I don't know if you can hear us. We can't see the screen, so if you can share that'd be...
Oh, all right, sure. Thanks.
Yeah, thank you.
Just make sure that I'm sharing the correct screen. All right, I guess all of you are able to see the screen now, right? Yep.
Looks good. Thank you.
All right, thanks. So yeah, what we started discussing is just that we have an announcement that lab 2 will be starting next week on Monday. And then today we'll be discussing more details about the op-amp circuits. And we have looked into a few different things in the past 2 lectures, that how to do this feedback-based analysis, come up with these 3 different forms of the equation, which eventually boils down to this. The closed loop gain of an op-amp system is the gain of the system, assuming that the op-amp is ideal, divided by 1 plus 1 over T, where T is the loop gain, and in the scenario that the op-amp is not ideal. So that kind of gives you an easy approach to tackle these kind of problems where the op-amp is not ideal, and you would still want to solve the problem within a short period of time. So that's one approach to do it. And we have looked into multiple different examples. For example, this was the example that you had seen earlier with non-inverting op-amps, that you have your input applied at the non-inverting terminal. You have a feedback provided to the inverting terminal of the op-amp. You just go ahead with the small signal or the linear equivalent model of the op-amp. In that case, you find out what is your A infinity, what is your T, and then you just put those particular values in place. Now, if it were a non-inverting ideal op-amp, there were multiple methods to solve it, and one very quick method, as I have already done in the class, is using the KCL approach or the nodal analysis based approach, where you'll just assume the virtual ground, that okay, you have this negative terminal here and a positive terminal here. The voltages at these two terminals, there would be no currents going in because the op-amp will have an infinite input impedance. So the current I minus is equal to 0, that current that goes in here, and you can calculate the other two currents and voltages accordingly, so that you can find out what is the overall gain in this particular system. So basically what you say is that your V minus is equal to Vs, that's from your virtual ground property, that the voltage at your negative terminal will be equal to the voltage at your positive terminal for an ideal op-amp, of course, and the voltage at your positive terminal is equal to Vs. So the V minus, that's the voltage at your negative terminal, will be equal to Vs. So what would be I1, the current that flows through this R1 resistance? The current that flows through the R1 resistance, that would be the voltage at this point divided by the value of the resistance from Ohm's law. So that will be Vs over R1. You know that I minus is equal to 0, so there is no current going in the op-amp, which will mean that whatever current is flowing through the R2 transistor will be the same current flowing through the R1 transistor. So I2 will be equal to I1. So this current coming in, that gets divided into two parts at this point, but the part that should go in the op-amp is 0 because the op-amp is ideal. So all the current flowing through the R2 transistor, R2 resistor, will be flowing through the R1 resistor as well. And you just solve those current and voltage equations to come up with this V0 over Vs, which will be equal to 1 plus R2 over R1. So that's the general formula for an ideal op-amp in non-inverting configuration. Similarly, we have looked into the inverting op-amp. Again, for an ideal case, you can find out the overall voltage gain just from the current and voltage equations. And again, you'll be using the same approach. You'll be using the virtual ground property, that whatever voltage is present at the positive terminal will be the voltage at the negative terminal. If the positive terminal is an AC ground, so this does not mean that you are actually grounding it. For most op-amp applications, it's just an AC ground, which means that you can apply a DC bias point, a DC operating point here, to make sure that the op-amp is in a region where it can provide you enough gain. So this is an AC ground, but we are doing an AC analysis in this case. So for all practical purposes, this is a ground for you right now. So if this is an AC ground, this point will also be an AC ground, and you can find out the effective currents and voltages, and you can come up with this equation of V0 over Vs, which will be equal to minus R2 over R1. So as you see that there is a negative sign, this is an inverting op-amp configuration. Also, you can say the same thing because your voltage is applied at the negative terminal of the op-amp, and the positive terminal is the AC ground. So this is the inverting configuration, and the previous one was the non-inverting configuration. And we have also looked into the scenarios when you have this inverting op-amp, but a finite op-amp gain, that the op-amp is not ideal. And in that case, you'll use the formula of A infinity divided by 1 plus 1 over T. A infinity is something that you already found out in the previous page. That's your A infinity, assuming that the op-amp is ideal. And you just solve what is your T by solving the voltage divisions in appropriate resistances, and eventually you'll get the loop gain as well as the overall closed loop gain for the non-ideal op-amp. Okay, so there are these are a few exercises for you to just practice these things, but these are very similar to your homework number 2, which I think most of you are already submitting this week. Okay. So, now next we are going to learn about a few more applications with op-amps. So we have only looked into inverting and non-inverting op-amps, but in the previous class, there was a question on how can we use this as a current amplifier, for example. And in fact, the last problem in your homework 2 deals with a current amplifier. You'll see that your output is a current and your input is a current, even though it is mentioned that the voltage gain of the op-amp is probably around 500. So how to solve those kind of problems, how to make sure that the op-amp works as a current amplifier mode. That's something we'll learn in the next few minutes. But before going there, I would like to draw your attention to a few other configurations. So one of them is called a voltage follower. What is a voltage follower? That you take your you apply your input to the positive terminal, and you take your output, put it back at the input negative terminal as a feedback. Now you already know that this is a non-inverting op-amp configuration because you are applying your input to the non-inverting terminal, right? And you already know that the gain of the non-inverting op-amp configuration is 1 plus R2 over R1, where R2 and R1 were resistances that were present in the previous version of the circuit, which we had just discussed, which was this, that you applied your input to the positive terminal, but you had this voltage division working as the feedback in the original non-inverting op-amp configuration. But now what we are saying is that there are no resistances. I am just taking this output and putting it back at the input negative terminal. That's all we are saying. So what you have is basically resistances R2, the resistance R2 to be equal to 0 and the resistance R1 to be equal to infinite. Because if you just want to short these 2 points, your R2 needs to be equal to 0, right? And because this point is not connected to ground anymore with the R1 resistance, it's another equivalent way of saying that the R1 resistance is very, very high, ideally infinity. So if that happens, what would be your equation in this case? That when you had this non-inverting op-amp configuration, your gain was 1 plus R2 over R1. Now we are saying that R2 to be equal to 0 and R1 is equal to infinite. So basically this entire term will go out and your gain will be equal to 1. And that's all we are saying in the voltage follower configuration. So if we again go back to the voltage follower, it says the gain is equal to 1. Even if you have a ideal op-amp, the A infinity value will be equal to 1. So whatever input you are providing, you will get the same output back. And that's why it's called a voltage follower or a buffer. That you get a gain of equal to 1, which means that your input will be equal to your output. So why do you use such a circuit in, like what's the practical use of something that produces exactly the same input? The practical use is that in most circuits that we'll be designing, like in the course or even in future, you'll see that this Vs voltage, instead of coming from a voltage generator, it may come from another circuit. Let's say you are designing a very complex multi-stage design, and just before this op-amp configuration, you have a voltage generator from which this Vs voltage is being generated. And that's not an ideal voltage source at all. Right? In this case, we are showing an ideal voltage source. But if this is not an ideal voltage source, it will not be able to drive any. So what we mean by driving is that let's assume that you have a voltage source. If it is an ideal voltage source, it will be able to drive a load, for example, let's call this RL. So whatever voltage I'm generating here, I'll get the same voltage at this point, right? That's an ideal voltage source because the voltage source does not have a series resistance associated with it. Now, if this voltage source had a series resistance associated with it, if you have an RS, let's say source resistance of RS, and let's just assume first that the RS is 100 ohms, whereas this RL is 10 kilo ohms. Even in that case, you'll have almost Vs voltage available at this point because it will be a voltage division between 100 ohms and 10 kilo ohms. And you already know from the voltage division theory that the overall voltage division would be 10K divided by 10K plus 100. That's the voltage that will be available at this point, right? But if this RS is, let's say 100 kilo ohms for some reason, that you have a very non-ideal voltage source, and that can happen while designing electronic circuits, that the source you'll be designing could be very much non-ideal. If this is 100 kilo ohms, then what would be the voltage division? The voltage division will be 10 kilo ohm divided by 10 kilo ohm plus 100 kilo ohms. And then you'll not have a lot of voltage available at this point across your load, right? So this is called a driving problem, that your source is not able to drive your load. Whenever your source has a high source resistance or a series resistance, it will not be able to drive your load, which means that across the load, you'll not get all the voltage. You'll get a pretty much divided version of the voltage, which in this case is 1/11, right? If you do this math. Question?
So it's possible to use an
Exactly, exactly. So what we'll do is that we'll put this op-amp in between. So let's just assume that this op-amp has enough driving capability so that it can drive this RL of 10 kilo ohm. And you know that the op-amp should be able to do that if the op-amp has a low enough output impedance. If it has an output impedance of 100 ohms, then the op-amp should be able to drive this 10 kilo ohm load. So you don't need to worry about the source not being able to drive the 10 kilo ohm load. So what you will do is that you'll put this op-amp in the voltage follower configuration here. I'm not drawing the entire configuration, but you can draw it yourself, right? That you put this op-amp in the voltage follower configuration, which looks like this. That okay, you apply your input at the positive terminal of the op-amp, you put it in the unity gain configuration, and at the output you will have this RL resistance. So you will connect this RL resistance at the output terminal. And assuming that the op-amp is, even if it's not ideal, let's say it's close to ideal, it will be able to drive this 10 kilo ohm load, right? That's the practical use of these voltage follower circuits. Questions? So you're saying how is the voltage division problem being addressed? Yeah. So where is the voltage division happening? The voltage, so again, you have to go back and draw the internal circuit of this op-amp. If you do that, you'll see that you have this voltage source, you have your RS. Where is the RS going? The RS is going into the positive terminal of the op-amp. How does the positive terminal of the op-amp look like? It looks like an open circuit, right? And you have this dependent voltage source inside, which is 1 times, in this case, because this is the gain is 1, so you'll write 1 times whatever input voltage you'll have at this point. So I'm calling this voltage as V in. What is the input voltage in this case? Even if RS is 100 kilo ohms, let's say RS is 100 kilo ohms, but because this point is an open, you don't get any voltage division here, right? So this point's voltage will be same as Vs. If this is Vs, V in will be equal to Vs. So the voltage that you generate, this is 1 times V in, which will be 1 times Vs. And that voltage will go through these 2 resistances. One is R0 and one is RL. Now imagine your RL is still the same, 10 kilo ohms, but your RO is 100. So at that point, at this point, the voltage that you create will be almost equal to V in, which is equal to your Vs. So you are kind of isolating the 2 parts. You had this 100 kilo ohm resistance and a 10 kilo ohm resistance. The problem was that you had a voltage division between the 2. Now you're isolating them by putting a buffer in between. And you'll hear this term whenever you're doing circuit design a lot, that just put a buffer in between. It will do an isolation and it will solve the driving problem. This is what it means by solving the driving problem or putting a buffer in between 2 stages or like just isolating 2 stages. So you use an op-amp or any kind of amplifier in a voltage follower configuration, and that isolates your source resistance and load resistance. So the problem that you had initially, that your voltage was getting divided into a very small factor at the output, that problem will go away if you put a isolator or a buffer in between. Okay, clear? All right, but very nice question. So yeah, that's basically the practical use of this voltage follower circuit. Inverting op-amp is again something that we have already looked into, so I'll just skip that. There could be a use as a summing amplifier or a voltage adder. How do you use it as a voltage adder? Again, it's very intuitive that, okay, instead of applying one single voltage at this input point, so let's say we are doing a inverting amplifier, right? So what is the gain that you expect from an inverting amplifier? Minus R2 over R1, where R2 is the feedback resistance, R2 is this feedback resistance, and R1 is whatever resistance you're connecting with the voltage source. Now, instead of connecting one voltage source and one resistance, you can connect multiple voltage sources and multiple resistances. So you connect V1 with R1, V2 and R2, V3 and R3, and Vn and Rn. So if you're doing that, what you're essentially doing is that at this point, you are adding all the currents, because at this point, remember that because this point is the positive terminal is a virtual ground, the negative terminal will also be a virtual ground. So what will be the currents flowing through R1 resistance? That will be V1 divided by R1. The current flowing through R2 resistance will be V2 divided by R2, because the right-hand side of all the resistances is a virtual ground. Right? So the left-hand side is V1, right-hand side is 0. What is the current going through? V1 over R1. Left-hand side is V2, right-hand side is 0. What is the current going through R2? That will be V2 over R2, and so on. Okay. So you have all these currents flowing through the different resistances, and all those currents will be added at this negative terminal of the op-amp. And because the currents will be added and then currents cannot go in the op-amp, all the current will flow through this R2 resistance. And if you again just do the math, you'll come up with this equation that your output is basically minus R2 times V1 over R1 plus V2 over R2, V3 over R3, and so on. So it's basically the same form that earlier your V0 over V1 was equal to minus R2 over R1 if you had only one voltage input. But now instead of only one voltage input, you have multiple voltages and multiple resistances. So the first term is still the same. You have this first term, which is the first voltage input, that is still same as what you had earlier. Earlier you had V0 over V1 equal to minus R2 over R1, or V0 equal to minus R2 over R1 times V1. This is the same thing you have as the first term. But you have summation of the other terms as well, because you're connecting all these voltages and resistances at the input side, so they will all get summed up using KCL. I'm just assuming that you guys, at this point, you guys are all very familiar with KCL, so I'm not doing the entire calculation, but this is how you do it, that you assume the 2 points to be at virtual ground, the positive terminal and the negative terminal of the op-amp. You calculate the currents, and all the currents will be V1 over R1, V2 over R2, V3 over R3, up to Vn over Rn. So at this point, you have a summation of all those currents because of KCL. And where would all the current go? All the current will flow through this R2 resistance, because the current cannot go in the op-amp. The op-amp has an infinite input impedance. So if all the current is going through R2, then you'll have, just by writing the KVL equations, you'll find out this. All right. So similarly, the next configuration is called a current to voltage converter. Or you'll see this in some books that it will be called a trans-impedance amplifier. Why trans-impedance? Because it transfers your input current to an output voltage. So current being converted to a voltage, so your output over input is voltage over current, which is impedance or resistance. So that's why it is called a trans-impedance amplifier, that your output is voltage and input is current. And if that is the case, you're just applying this current at the input. Let's say you have this current source IS connected at the input, and you have the same, very similar configuration as before. But now, instead of having a V1 and R1, instead of having a voltage and a series resistance, you just have the equivalent current flowing into this terminal. So it's exactly still the same. It's just that instead of showing voltage and a resistance, we are just showing a current. So it's the Ohm's law equivalent of the previous non-inverting amplifier circuit. That instead of applying a voltage at the input, you're applying a current at the input. So you don't know that you don't want that resistance anymore because you already have it in the current form, in the form of a current, and that current will entirely flow through the R2 resistance. What would be the gain of this circuit? Yes, question. There could be a parallel source resistance. Yes, that's a very good question. But that parallel source resistance will affect your calculations only if this amplifier is non-ideal. Right? If it is ideal op-amp, it will not affect your calculation because this is a parallel source resistance, but this impedance is infinite. Looking into the op-amp, the impedance is infinite. So in this case, what would be your A infinity? What would be the gain of the system? Remove all of this. So again, I'm assuming that all of you should be able to solve KCL and KVL at this point, but I'll still go through this. That okay, you have a IS current coming in. Where is that IS current going? It is entirely flowing through R2. What is this point's voltage? This point's voltage is equal to 0. Why? Because the other terminal, that point's voltage is also 0, AC 0. So it's an AC virtual ground at both the positive and negative input terminals. So if this point's voltage is 0 and this point's voltage is V0, and you know that there is a IS current flowing through R2, then what is the voltage at V0? It should be minus of IS times R2, right? That should be equal to your V0. Why? Why are you saying that? Because this point's voltage is 0, this point's voltage is V0. So I'm writing the voltage division 0 minus V0, and I'm dividing that voltage division, the voltage difference with the resistance R2. That would give you the current, right? So this is your current IS that is flowing through R2. So again, just applying Ohm's law, nothing else. So which means that your minus V0 equal to IS times R2, which means your V0 equal to minus IS times R2. So what is the transimpedance gain? What is V0 over IS? The transimpedance gain is equal to minus R2 in this case. And that's what we are showing here. That your A infinity, assuming that the op-amp is ideal, your gain, transimpedance gain is equal to minus R2. Now, keep in mind that in the previous few cases, your gain was minus R2 over R1 or 1 plus R2 over R1. So you had a ratio of resistances. A ratio makes it unitless, right? Whenever you have a ratio, the ratio is unitless. So if it is minus R2 over R1, it's a unitless quantity. That's why it's a voltage, output is a voltage, input is a voltage. Voltage over voltage is a unitless quantity. But in this case, I'll just come to your question, but let me finish this. That in this case, your output is a voltage, input is a current. So your gain is voltage over current. What is voltage over current? It's a resistance. So that's why you see that your A infinity, that the gain of the system has the same unit of resistance. Okay, question. Where are the two negatives? So V0 is equal to minus IS times R2, but IS is not negative, right? Oh, okay. So IS is this current flowing in. It does not change direction. So it still flows in the same direction. So if you're not assuming a different direction for IS, it does not have a negative sign. Any other question here? All right, perfect. So next, we'll look into current mode outputs. That okay, you can have an input current and an output current. Even though the op-amp, we are defining it as a voltage controlled voltage source, your input could still be a current, output could still be a current. So for that, you will put the load in series with the feedback signal path. So what does that mean? That you have this. So let's just assume this particular scenario. that, okay, you were calculating the V naught, right? You were calculating the V naught over here, and you had this R2 connected in feedback to the input. Now, let's just assume that your output is a current. What does that mean? That means that from this point V naught, at the you could have connected an ammeter, which is another series resistance at this point, and calculated what is the current flowing through that ammeter. So if you connect an ammeter at this point in series, so whenever you want to measure current, you have to connect an ammeter in series, right? Whenever you want to calculate the voltage, whenever you want to measure the voltage, you have to connect a voltmeter in parallel. So in this case, if your output quantity is a current instead of a voltage, you have to connect an ammeter in series with whatever feedback connections you are making here, and then you'll calculate the output current divided by input current. That would be your current gain. So a variant of this is provided in your homework number 2 as the last question, that it had an output current divided by input current. That's the quantity that you need to find out. But the analysis will still be same. Analysis can be done using this KCL, and then you can apply the formula of loop gain to figure out what's the overall gain of that system. So just like you can always convert currents to voltages, please do that while you're solving that question in that homework number 2, sorry. You can also do a voltage to current conversion, that your input is a voltage, but output is a current. So this is one example of this, that, okay, your input is a voltage, you're providing that voltage input to the non-inverting terminal. You have this ZL and R1 connected in feedback, and the current through ZL, because ZL is the load resistance, the current through ZL is your output current I naught. So in this case, what is your gain? The gain is current I naught over voltage Vs. So this is called a transconductance amplifier. Because your output is a current, input is a voltage, current over voltage is a conductance. It's 1 upon resistance, right? 1 upon resistance is conductance. That how much conductive you are instead of how much resistive you are. So this is called a transconductance amplifier. And this transconductance amplifier, in this case, this is I naught over Vs, right? So I naught over Vs is something that you can calculate as the gain of the system. And assuming that this op amp is ideal, you'll call this A infinity, right? So that will be your A infinity. Now, what would be your I naught? And keep in mind that you're defining I naught in this direction. So if this point's voltage is Vs, due to virtual ground property, or because the op amp has a very high input impedance, this point's voltage will also be Vs, right? The negative terminal will also be Vs. Which means that the current flowing through R1, current flowing through this R1 resistance will be Vs over R1. Vs divided by R1. That's the current flowing through the R1 resistor. Where is this current coming from? The current is exactly same as this I naught current, because as this I naught current is coming in, it will get divided into 2 parts at this point. One part will go to ground, and the other part will try to go into the op amp. But because the op amp has an infinite input impedance, there will be no current going into the op amp. So the entire I naught current is flowing through R1. And we already know what is the current flowing through R1, that is Vs over R1. So this will be equal to your I naught. So if Vs over R1 is equal to I naught, what is I naught over Vs? That will be 1 upon R1. What would be your I naught over Vs? I naught over Vs will be equal to 1 upon R1. And that's a direct relation you can find out from the previous equation. All right. So similarly, you can also use it as a current buffer, that your input is a current, output is a current, and you want a current gain of equal to 1. How do you do that? This is probably the easiest one out of the lot. That, okay, you have your input current over here, and all of that input current will be flowing into the output if this is your output load. So because all the current is flowing at the output from the input side, the current at the output divided by current at the input is equal to 1. So that's an example of current buffer. You can do a current amplifier by doing a judicious current division. So in this case, we are not doing any current division. That's why the current gain was equal to 1. But you can make it a current amplifier by doing a judicious current division. So in this case, how it is being done, and again, this is just an example. There could be multiple other ways to do the current division or the voltage divisions, as you already know. In this case, how you are doing the current amplification is that you have an input current at this point, at this node. This node is a virtual ground. Why? Because the positive terminal of the op-amp was also a virtual ground. So this point, the negative terminal of the op-amp is also a virtual ground. But no current can flow into the op-amp. So all the current that you're pushing in will flow through this path. What would be your V3? What would be the voltage at this node? Voltage at this node will be this point's voltage minus the current that is flowing through the R2 resistance multiplied with the value of R2 resistance. What is the voltage at the left-hand side of the R2 resistance? That is 0 because of the virtual ground property. What is the current flowing through the R2 resistance? That is equal to IS. So what would be the voltage at the right-hand side of the R2 resistance? That would be 0 minus IS R2. Okay. So you know that V3 will be equal to minus IS times R2. If V3 is equal to minus IS times R2, what would be I3? What would be the current flowing from V3 to ground through this R3 resistance? That would be V3 over R3, which will be equal to minus R2 over R3 times IS. So you'll know that what would be your I3. What would be your I0 then? Because you already know that there was an IS current coming in. Some part of it is flowing to ground as I3 through this R3 resistance, but the rest of it is flowing through the ZL resistance. So what is the rest of that current? The rest of the current is I0, which is IS minus I3. Some current went through R3 to ground, but rest of the current is flowing through ZL. What is that rest of the current? That is IS minus I3. And now we can put the values of IS, the value of I3 over here as a function of IS. So you will get a ratio of I0 over IS. And I0 over IS can be written as 1 plus R2 over R3 in this configuration. So if R2 is much larger than R3, you'll get a current gain. So even though your op-amp is still a voltage controlled voltage source, you're getting a current gain out of it. Your output is a current quantity, input is a current quantity, and you have a current gain. So it all depends on how you define your input and output quantities. It does not matter what the ideal op-amp is about. Questions? Which one? I3 is equal to minus R2 over R3 times. This is from this equation, right? And you're asking why this negative sign is present, why this is negative. This is negative because your V3 is negative. The left-hand side of R2 resistance is 0. But still the current is flowing towards right. What does that mean? That the right-hand side is more negative than 0. If the left-hand side is already 0, still the current is flowing from left to right. That means that the right-hand side is more negative. And that's why the value of V3 is minus IS times R2. Questions?
In the case of the homework where we have a question like this,
yeah,
we're asked to find the loop gain T.
Yeah. So this just finds your A infinity. It does not find out loop gain. So now to find out loop gain, you have to assume that this op-amp is a non-ideal op-amp.
We use a linear
You
model.
find the linear model, you do the beta analysis and find out the loop gain.
How would we do that if we're given the gain? Like we use just the AV is equal to 500. That's given.
Yeah, yep. All right. Okay, so now the next part of the op-amp discussions that I wanted to have is that there are other non-idealities as well, except for the non-infinite input impedance, non-zero output impedance, or non-infinite gain. Those are the three like very common, just by definition, because you know that the ideal op-amp has infinite input impedance, infinite gain, and zero output impedance. You know that if we're talking about non-ideal op-amp, it means that those three conditions are not being satisfied. But apart from that, there are other non-idealities as well in an op-amp. So as you'll see during your lab 2 or later labs as well, that the op-amps that we have selected, the LM741 or the 3310, so both of them are, of course, not ideal because they are a real circuit, a practical circuit, right? So what are the other non-idealities that you can expect from an op-amp? One of the major non-idealities that you do expect from an op-amp is called an offset voltage. What does the offset voltage mean? Remember that when you talked about ideal op-amps, we said that the input versus output characteristics look something like this. Let's say this is the out, this is the in. And let's just for a moment assume that we are not doing any signal inversion here. So if you're applying a small positive input, your output is a large positive output. And then it will saturate, right? Because of the VDD and VSS rails. Similarly, if you apply a small negative input, you will observe a large negative output, and then it will saturate again, right? That's what we told that the ideal characteristic of the op-amp looks like. But because of the offset, this ideal characteristic can be shifted a little bit. That's what you're seeing in this right-hand side plot. That even if you're not applying any input, the output of the op-amp is stuck at very high value. As you are start to apply some negative input, at some point you'll see that the op-amp's output will start reducing, and then you'll see that this curve is being followed, but in a shifted manner. Question? No, it's not because of capacitance. It's because something that is more involved, like much more complicated than that. And we'll learn about that in this course later on when we actually discuss MOSFETs and BJTs. That why does this offset come in? But for now, keep in mind that any op-amp can have an offset, which means that, okay, if you apply zero input voltage, what is the output voltage do you expect? Zero, right? You multiply a gain with zero, you should get zero. But if you apply zero input voltage, you may not get zero. Just connect the op-amp to its VDD and VSS. Don't apply anything at the input, or just apply a fixed bias at the input. So for example, let's say this op-amp has a plus 5 volt VDD and minus 5 volt VSS. So the DC bias that you may need to apply is around 0 volt. So even if you don't connect anything, you'll see that the output of the op-amp will be either plus 5 volt or minus 5 volt. And that's not expected, right? Because you expect the output of the op-amp to be gain multiplied with the input voltage. That will not happen in a practical op-amp that you buy from the market because of the offset scenario, or because there would always, it is usually modeled as this, that you have an offset voltage at the input side, which we are marking as VOS, V offset. And that offset voltage results in this kind of a shifted input output characteristic for the op-amp instead of having something like this. All right, so you don't need to go into too much details of the offset at this point, but just keep in mind that this is something you may be seeing in some of your experiments. Question? A few millivolts is definitely a very realistic amount of offset. Usually it's in the range of, let's say, 5 millivolt or so. It could be as large as 10 millivolts in certain cases. So if the op-amp, so it's interesting though that if your op-amp does not have a gain of, let's say, infinity, if it has a gain of 10, then you'll multiply that gain with the offset voltage, and that's what you'll see at the output side. Okay, I think, yeah, there are some more details about the amplifier offsets over here, which you can just go through. Mostly the value of offset is random. So if you choose one op-amp versus another, so your op-amp and your friend's op-amp might have a different offset voltage. Your op-amp might have 5 millivolts, your friend's op-amp might have 4 millivolts. And there is no way to control that because this offset mainly arises from manufacturing non-ideal. And when you manufacture these electronic components or devices, you'll see that some of them will have random fluctuations, and offset is a result of some of those random fluctuations in the manufacturing process. So what really happens is that I'll give you a glimpse of what we will be discussing maybe like 10 or 15 lectures down the road, that you have this as an op-amp, right? That you have a positive terminal and negative terminal. What is there inside that op-amp? Inside the op-amp, there are devices like MOSFETs or BJTs, depending on whether it's a CMOS-based op-amp or a BJT-based op-amp. Let's just assume that it's a MOSFET-based op-amp. The way you draw MOSFETs or the symbol of MOSFETs, this is an N-type MOSFET. We'll again discuss what N-type MOSFET is later on, but this is how it looks like. So you have one N-type MOSFET connected at the positive terminal. So basically this input comes at the gate. This is called the gate terminal of the N-type MOSFET. So this input comes in at this gate. And why do you say that no current can go inside the op-amp? It's because for this, the way it is drawn is that, okay, you have a line over here and then another line over here. Why you are not drawing in between is that there is an insulator layer. We'll discuss about all those things when we discuss MOSFET. That there is an insulator layer in between, and that's the reason why no current can go in. That's the actual reason why no current can go in the op-amp. That there is an insulator layer in between if you're implementing this in the MOSFET. Similarly, there will be another MOSFET at the negative terminal. Now, this MOSFET and the other MOSFET, which is connected, let's say this is the positive terminal MOSFET and this is the negative terminal MOSFET. These MOSFETs are not the same ones. And whenever you are building two different MOSFETs, there will be some manufacturing variation between them. This will not have the exact widths or lengths or exact connections as this one, even if you intend it to be. Right? It's same as let's say you are designing the circuit on a breadboard and your friend is designing the circuit on a breadboard. Even though you are designing the same circuit, would it exactly look the same? Maybe not, right? And most likely not. There will be some variations in the wire lengths. There will be some variation in the point in the breadboard that you connect your circuit, and so on. And it will create two non-idealities. And the manifestation of those non-idealities in case of a op-amp eventually results in this offset voltage. We'll discuss about this more later on, but right now keep in mind that this is just a random fluctuation, and it is present in all practical op-amp circuits. Okay, so I guess I think we can stop here today. So it's just that you have more details about some of the offsets and the effects of offsets over here. Please go through the notes, but it's mostly about how do you analyze those offsets in terms of a voltage or current. Okay. In the next lecture, we'll be discussing about op-amp frequency response, and that's when we'll conclude the discussions on op-amps. And after that, we'll start our discussion on diodes.